In this problem, I'm gonna find K equilibrium constant at 250 Celsius. So K equal, in our reaction, the products are carbon monoxide and hydrogen. At equilibrium, we are supposed to find the concentration of these two, and they both go on top as a rule, and the methanol, which is our reactant, has to be in the bottom. And don't forget the coefficient in front of hydrogen, which is going to be raised to second power. If it had the third 3, then it would have been the third power, cubic power. Yeah. We're given mass of methanol, volume, and temperature. You're gonna we can put the volume within our K equation. Then you will have this. Ultimately, we want to find this. To find the number of moles of carbon monoxide and hydrogen and methanol at equilibrium, I'm gonna first create the ice chart. I stands for initial, C stands for change, E stands for equilibrium. But unfortunately, they gave us the mass. So since you cannot directly put this into the ice chart, I have to convert this to number of moles. To do that, you have to find the molar mass from the periodic table, and if you do this right, you should get 32.042 gram, and that's 1 per mole of methanol. You're supposed to get 0.147 mole of methanol. So I'm gonna put that as our initial. Then I subtract and add accordingly to our stoichiometric coefficient. Oh, I forgot 2 here. You add plus 2x, and you want to add these up. And here we get the equilibrium concentration that's going to go directly into our K equation in the red font here. So I'm going to use different color. So this X stands for the number of moles of carbon monoxide, number of moles. 2x stands for number of moles of hydrogen, and 0.147 minus x is the number of moles of methanol. Of course, these are all in equilibrium. Okay, now we're gonna, to find x, we're gonna move on to the next piece of information they gave us, the question gave us. That is, we need to use law of diffusion. From the law of diffusion, we can find the mole ratio. But to illustrate that, let's first assume 1-to-1 ratio. Okay, because they gave us the hydrogen and methanol, that's our study. Imagine you have 1 mole of hydrogen interacting. Could be 1 mole of hydrogen, 1 mole of methanol is found in the flask. Then we are supposed to find the rate based on the grams law of diffusion. Okay, so diffusion is like you make a hole, very tiny hole, and we are observing how much one molecule is more frequent than the other. So rate of the general rule is a rate of 2 over rate of 1, the first molecule and second molecule, and they have an inverse relationship with each own molar mass, and we expect like that. Because we are studying the hydrogen and methanol, I'm gonna put the rate of hydrogen on top, rate of methanol on bottom. Okay, the molar mass of hydrogen gotta go on the bottom here, 2.016, and methanol you should get 32.046 grams per mole. Well, the units actually cancel out, and we're gonna see the ratio to be 3.9867. So what this tells us is every one molecule of methanol goes out of our flask, we expect about 4 molecules of hydrogen to effuse out from the flask. Okay, but then that's not what we see from the problem here. It said the measurement of the effusing gas showed that it contains 33 times as much as that. Okay, so in reality it's not gonna be 1-to-1 ratio. Okay? Let me illustrate that very simply, because say you have same volume, but different number of molecules. This is very simple model, so I'm just trying to illustrate my point. So say 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have a 9 white gas molecule, and I say I have a 1 black and 1 white here, and I make a hole here, tiny hole. See, if you have more moles, you expect the effusion to be higher rate, right? So it's like a 90% here versus 50% here. So it's the same concept apply to our problem. So in other words, the rate, as you saw from my diagram, rate is directly proportional to number of moles or molecules. Okay, then going back to our ratio. Okay. Our rate, this is observed in our experiment, was 33.0. Right? So from here to here, and I'm also gonna write more. So it's a 1-to-1 ratio. I really don't know. I wanna refine x here. Okay, I just defined that their relationship, directly proportional relationship. Okay, so from here to here, you have to multiply, or if you divide this by that, you're gonna get what? From calculator, you should get 8.2775. Okay, check you multiply this much. Since we see more hydrogens, we have more moles, the same thing applies from here to here. If you multiply that, you are also multiplying 8.2775. In other words, every 1 mole you see from the effusion, every 1 mole of methanol, you're seeing 8.27 mole out of it. Okay. So let me restate that, and we're almost to the answer now. That X turned out to be 8.2775. Okay. I'm just keeping extra digits and I'm gonna round up at the end. And where did we see this? Okay, remember this is at equilibrium. Then you go back to our ice chart. Okay. Do you see that 2x hydrogen and 0.147 minus x? Well, we can directly put them in our equation. So 2x on top, okay, that matches. And on the bottom, I have to have 1.47 minus, I believe it was x. Yeah. Okay. So from here on, it's a simple algebra. Okay. Because I don't want video to be too long. At this level, you should be able to cross multiply and then find x. Okay, I'm gonna leave it up to you. Okay, you should find x equals 0.1183 mole. Okay, so find x by algebra. Okay, you're gonna get that, and then what you do is, okay, plug it in to our equilibrium concentration at in our ice chart, 0.1183, and you multiply it by 2, you should get 0.237 mole, and you put okay, when you plug it in and subtract it, you should get a 0.029 mole. Okay. And then you plug these values, plug these into our K. Goes here, goes there, and goes there. Okay, make sure you put the right stuff. When you plug them in, okay, you're supposed to get 0.23. Now let me clarify about the sig peak. You might say there doesn't seem to be a lot of addition and subtraction, and you have 3 sig peaks, and it's easy to just make it 0.231 if you do the calculation right. However, you're gonna notice in our ice chart for the methanol that when you subtract x here, x turned out to be a 0.1183. Even if you keep that many sig peak, what happened is that 1 and 1 cancel out, you have 0. But since we have 3 sig peak, it can only go up to thousandths place. That 0.029 has only 2 sig peak, and that's why in the end, when you do the multiplication and the division, you get only 2 sig peak. I believe most teachers won't care if you have 3 sig peak, but I'm just being very accurate. So your final answer should be 0.23. Okay, so it had a lot of steps, and especially you had to think I think the key to solve this problem was not only the forming the ice chart, but also combining the concept of law of effusion, Graham's effusion, and then see the rate and the number of moles have a directly proportional relationship. So that was it, guys. So thanks for watching.